So Dr. A. Hemalatha, she will be speaking on evaluation of out-of-field dose associated with flattened and unflattened X-ray beams using Mosaic detectors. So let us see. I think she has. Are you ready, madam?
Yes, ma'am. Yes, ma'am. We just connected.
Okay, okay. So in this particular our session, so many lectures were there and all were mostly different from each other. Different fields were there. So I think this is the beauty of any seminar, that we are getting information from all sectors, from all fields, even if we are not working on that particular field. So that is a remarkable thing in this particular seminar, I think. Okay, I think she has come on the dais. So Dr. Hemalatha, are you going to start now?
Yes.
Okay, okay, no problem.
So my presentation is about evaluation of out-of-field dose associated with flattened and unflattened clinical X-ray beams using MOSFET detectors. So this is a preliminary study I have carried out in the clinical medical linear accelerator, that is in our radiotherapy department. So what is the purpose of the study is that as we know that so many modern technologies have happened in delivering radiotherapy treatment and also in the treatment planning system. But this improved that conformity or improved modern technology still it is not mitigated the dose to the outer field organs. So the physicists are in way to find the how to reduce the dose to outer field organs. So this is the one of the method we are measuring the outer field dose. So and we are finding the way how it can be reduced so the patient can be benefited.
कैमरा सेलेक्ट कर दो शुरू से करें
वो नहीं
अब करें हो रहा है
Introduction. So as the clinical use of flattening filter-free photon beam increases in radiotherapy, the need for in-depth characterization of triple F beams is arisen due to the inherent differences in beam properties from the conventional flattened beams. So the triple F is one of the advanced treatment modality available in the linear accelerator machines. So the reported benefit of the unflattened beams compared to the flattened photon beam is that it is very small. Compared to the flattened photon beam is at increased dose rate, reduced scatter and leakage radiation, and a reduction in the outer field dose. So what is the outer field dose? It is defined as the observed dose that is outside the radiation treatment field border. So the outer field doses arises where it is coming is that it is a leakage radiation from the head of the treatment unit and the scatter radiation from the collimator head and beam modifiers. Also it is contribution from the internal scatter within the patient. So the outer field dose may be clinically significant. So when it is significant, when the dose to the fetus or to the organs with low dose tolerance are nearby the critical structure, nearby treatment field. So it is also relevant when considering the risk of second malignancies or the potential failure of the implanted electronic devices like pacemaker, the patient with the pacemakers or defibrillators. In that case, we have to reduce the dose to these devices and dose to the fetus or other critical organs. So there are, due to unknown accuracies in the outer field dose calculation with a commercial treatment planning system that we used for treatment planning. So it is essential to assess the outer field dose through the phantom measurements or Monte Carlo stimulations. So my aim of the study is that to evaluate the outer field dose associated with flattened and unflattened X-ray beams using the MOSFET detector. So MOSFET is a metal oxide semiconductor field effect transistor detector used in for radiation dose measurements. So this is the importance of the flattened and unflattened X-ray beams. So here we can see that the first picture is the radiation beam without the flattening filter, and second one is the radiation beam with flattening filter. So initially, most of every machines it comes with a flattening filter to flatten out the beam so that we will get a uniform dose distribution in the treatment volume. Later on, the flattening filter is removed to increase the dose rate so that we can reduce the treatment time. So the first picture is the dose distribution in the treatment field without flattening filter. So the material method and used for this study is that linear accelerator machine, that is medical linear accelerator machine, the true beam machine, and the beam energy we have selected for the measurement is 6 and 10 MB, flattening filter beam and without flattening filter beams. And the detector used this metal oxide semiconductor field effect transistor from the Canada, Best Medical Canada. And the chip, it is the MOSFET is nothing but it is a measurable device. It is an electrical device with a silicon chip of 1 mm square, and the active area is 0.2 mm into 0.2 mm. So it is a device used to this. So this is the device, and this is connected with the remote dose verification system through the mobile through the wireless Bluetooth system. And the phantom is solid slab phantom used, and it is made up of the dimension is 30, 60 into 20 centimeter cube. And the method of measurement is that the measurements are carried out for the 3 different clinically relevant field sizes, that is 5 by 5, 10 by 10, and 15 by 15 centimeter square, under the depth of D max 5 centimeter and 10 centimeter. So this is the schematic diagram showing how the measurements were taken. And so from the field edge, we have taken up to the 30 centimeter from the field edge. What is the contribution from the leakage and scatter radiation? So from the field edge, it is taken up to 30 centimeter. And for 3 depths, we have taken D at the depth of D max 5 centimeter and 10 centimeter. So these are the results of our study. And for the depth D max and for the 5 centimeter and the 10 centimeter, the out of field dose from the field edge, it is shown that 6 MB that is for flattened beam, and for unflattened beam, the unflattened beam, that is out of field dose or leakage or scatter radiation associated with unflattened beam is lower than the flattened beam. So it is the advantages of that triple F beam. So it is proven for all the depth of 5 centimeter and depth of 10 centimeter in both 3 measurements. It is shown that the unflattened beam have a lower scatter and leakage radiation compared to the flattened beam. So similarly, the measurement is carried out for the 10 MB flattened and unflattened X-ray beam. So in the 10 MB, that is in the higher energy, with the higher energy also, the triple F beam is associated with the lesser scatter and leakage radiation compared to the flattened beam. So this is one diagram showing the comparison between the 6 and 10 MB flattened beam, unflattened beam. So here we can see that the higher MB have a higher energy having a lesser leakage and scatter radiation compared to the lower energy, because lower energy will have a greater contribution of leakage and scatter radiation compared to higher energy. So discussion part, from this study, we have observed that out of field dose, that is scatter and leakage radiation from the head and the other parts of the machine, it is associated with 6 and 10 mm flattened beam is higher than that of unflattened X-ray beam, and it is also decreasing with increasing distance from the field edge. So when you're going away from the field, the out of field dose is decreasing, and the field size is decreased. When the field size is decreased or the treatment volume is decreased, the out of field dose is decreasing. So in a modern radiotherapy, the treatment delivery is feasible without flattening filter for IMRT and stereotactic radiosurgery treatment. So in the advanced treatment like IMRT and SRS-SRT, now we are more preferring to give treatment without flattening filter, because it the advantage of dose rate, we can deliver this treatment within a few minutes with a triple F beam, because it few seconds, because the triple F beam have a higher dose rate, nearly two to three times higher dose rate with the triple F beam. So triple F beam we can deliver nearly 1400 to 2400 MU, means MU means nearly 25 centigrade and 25 gray can be delivered in a minute. So in addition to drastically increasing the dose flattening filter modality, it also reduces the out of field dose as highlighted in the results. So because it reduces the head leakage, because less target current is required in the triple F mode. Similarly, collimator scatter also reduced, because the flattening filter is a no longer source of the scatter. Since the flattening filter is removed, the main contribution from the collimator scatter is reduced. So conclusion, so the dose to the outer field organs at risk and electronic implanted devices like pacemakers can be estimated using the measured outer field data sets. So it is not suggested to rely on radiotherapy treatment planning system data instead of measurement values, since it is not commissioned for the outer field dosimetry. So radiotherapy treatment planning system, we use it for the planning of radiotherapy patients. So that data can be relied only for in-field treatment volume, how much dose is going inside the treatment volume, but outside the treatment volume, how much dose is going, it is not exactly commissioned in the treatment planning system. So from the TPS, we cannot estimate exactly what is going outside the treatment volume. So in addition, the Mumbai MOSFET used is compact, and it has a rapid online readout and lightweight, and it is appropriate for doses assessment in the outer field region. So the triple F beam is most beneficial in terms of reduced head leakage, and is therefore most advantageous for cases using higher energies, smaller fields, and intensity modulation. And it also offers the greatest dose reduction far from the treatment field. So triple F delivery is an improvement in modern radiotherapy. So it can be used for IMRT treatment delivery, like advanced treatment for SRS and SRT. It can be implemented. So these are the references we have used for this study, and I wish to acknowledge my guide, Dr. Arun Chandra, and my department radiotherapy and radiological physics department, and R.K. Provit sir, and other organizing committee members for giving me this wonderful opportunity. Thank you.
Thank you very much, Dr. Hemalatha. It was a nice lecture. Any question? Quickly, one question, because we are running 1 hour late. Anyone? Offline, online, whoever want to discuss anything? One question only. Thank you very much, Dr. Hemalatha.
Thank you.
So I thank other chairperson, Dr. B.S. Rao, and had the opportunity to call here Dr. Pratap Singh, because it is a long session. Are you there, Dr. Pratap Singh?
Yes, ma'am. Yes, ma'am.
Okay. I hand over the mic to you, please.
Yeah, thank you very much, Professor Hemalatha. It's a matter of great privilege to thank all the participants who have joined this session online as well as offline. The third session on clinical radio protection was chaired by Dr. B.S. Rao from Mumbai and Dr. Vinika Shukla from Rohtak. I'm very grateful to both of them from all the organizers that they very smoothly run this technical session. I'm also grateful to Professor Eva Bezek, who is Director Center for Translational Cancer Research, UniSA Cancer Research Institute from South Australia, and the team in Mars, which included Dr. Amit Alok, Dr. Vanita Gupta, and Dr. Ajasprata Datta. Dr. Shuchi Bhagi and Dr. Shravan Kumar Singh. We are very grateful to them that they all participated and their lecture was very well received by the audience. I'm also grateful to Dr. Hemalatha from SPMC, Bikaner, for delivering her lecture. And I'm also grateful to all the audience who have joined online as well as offline, and all the faculty members of Bloomberg College who have participated wholeheartedly to make this international conference on radiation biology 2022 a success. Thank you very much from the bottom of my heart. Thank you.